Unit 3, review, probability, part 2, examples worked out. All right, turn to this part of your packet. And let's go ahead and work all the different examples out. Okay, so we've got complement, just means 1 minus, so the probability of A is 0.35, so 1 minus 0.35 is going to be 0.65. Probability of A or B, that's all of A, which is 0.35, plus all of B, which is 0.6, minus the overlap, which was 0.27. And this formula is on your formula chart. And that gets us 0.68. Probability of A given B, on the formula chart, that's probability of A and B over probability of B. And so if we go ahead and do that, A and B is 0.27 over probability of B is 0.6. And so that's going to be 0.45. Are A and B independent? Well, for A and B to be independent, probability of A given B has to be equal to probability of A, or I could look at it as the probability of A and B has to equal to the product. Well, we've already looked up above, and the probability of A and B is equal to 0.45. The probability of A is equal to 0.35, so no, it is not. And the reason being is because these two here are not equal. Okay, let's look at example 1. Suppose the probability of a construction company it will be awarded to the contract of 0.25. Let's continue here because I'm sure you've read it. It says, what's the probability that the company will win at least one? Whenever you're doing at least one, we're wanting probability of at least one equals probability of 1 minus the probability of none. So we have the probability of at least one, which is going to be 1 minus probability of none, but it's saying that means I'm going to get probability of A or B, so I could get contract 1 or contract 2. Oh, hold on, it's not 1 or 2. So contract 1 or 2, well, probability of contract 1 is 25%. Probability of contract 2 is 21%, or I guess A or B. It's contract A and contract B, or contract 1, contract 2, doesn't matter. But minus, it says the probability that I am going to get both contracts is 13%, so that got counted twice, so that's going to be probability of A minus the overlap, which is 0.33. Example 2, you're going to ask for you to read this chart and then find the probability. What is the probability that from the student what is the probability that a student from this group fails the math program? Okay, so from this group, when it says what's the probability, and as soon as it says from, that's going to be the denominator. And so the denominator here is 2,000, so that's my denominator. So it's something out of 2,000. And it says from this group, so fails is this amount, so that's 200. The next one, what's the probability that a student from this group, so again, this is from this group is going to be 2,000, fails the math program, but it says given, there we go, she has blue eyes. So every single person in my group is going to have blue eyes. So it's from this group, however, I'm going to get blue eyes, and you could do it with the formula, or you could just go quickly and say, okay, of the blue eyes, how many failed? And that's going to be the 10 of 100. Are blue eyes and failing independent or dependent? So in order for them to be independent, now remember, if I did this part here, this would be the probability of fail. And this is the probability of fail given math. This is 10%, and this is 10%. And if the probability of fail given math is equal to the probability of fail, then yes, indeed, they're independent, and they are both equal to 0.1, so yes, they are independent. That is all that you would need. You would say, if on an AP test, you would say that exactly. If, I would put if probability of fail equals probability of fail given math, then they're independent. Or you could say if they're independent. It doesn't matter because they're a biconditional statement. And then you would show your work and show indeed they are, so yes, independent. For number 3, I'm going to have you go ahead and read through those, but I'm going to go ahead and put this in a chart. And the chart I'm going to use is high blood pressure, yes, no. So this is high blood pressure. And this is type 2 diabetes. So I'm just going to put that yes, no. And if you read through it, let's go ahead and read through it. And you see that you have 60 teenagers, 60 obese teenagers are in your study. And then you go and it has 15 has type 2. Oh, that says no, sorry, I'm in the wrong column. I need one more column. Total. So that's 60. And then 15 has type 2, which obviously means that's 45 does not have type 2. And it says 20 has high blood pressure, so that's obviously going to be 20 and 40. Then it goes and says 10 had both. So 10's here, and now we can just do some math. So this is going to be 5, this is going to be 10, and this is going to be 35. So that was just all done from just a little bit of a math work for me. And then I'm going to say, this says, given it has type 2, they have type 2, what's the probability they also have high blood pressure? So given type 2, what's the probability of high blood pressure? So I'm going to put high, given type 2. That means the only people that I want here have type 2 because that's my denominator. So I go here to type 2, and so the denominator is going to be 15, and I see how many of those 15 people also have high blood pressure, and that's 10, so that's 10 over 15. So this one says, the next one says, if the obese teenager does not have high blood pressure, so I'm going to quickly kind of show you the same thing. Let's go 10, 5, 15, 10, 35, 45, and 20, 40, 60. This was my yes, no. These are for type 2. Yes, no, and that's total. And this is for high blood pressure. So this one says if the obese teenager does not have high blood pressure, so they do not have high blood pressure. So the ones that do not are these here. So my total is going to be 40 on my denominator because I'm looking for what's the probability he also does not have type 2. So I'm looking for type 2 given high blood pressure or not high blood pressure. And so we know the denominator is going to be 40. And so type 2 is going to be, it says that that also not type 2. So the not type 2 is going to be here. So that's going to be 35 out of 40, which is 0.875. And this one here is 0.667. It's a good idea to go all the way to the decimal just because then if it asks if they're independent, they match easily. Example 4. Okay, it says the probability that Michael misses a free throw shot is 0.1. That's his probability. If he goes to the line to shoot free throws due to a foul on a three-point line, what's the probability that Michael misses all of them? So missing all of them is going to be this is the probability of miss. So it's going to be 0.1 to the 3. So you'd say probability x equals 3. And that's obviously going to be 0.001. What's the probability that he makes at least one? Well, making at least one means I'm going to make one and miss two. Or I could miss this one. Or I could miss this one. Or I could make these two, and so forth and so on. So I got to kind of get all of my options, but I don't have time to do what I'm doing because it's making at least one. So what I'm going to do is I'm going to use a binomial formula. The binomial formula, remember, tells me I have 3 shots. I want to make at least one. The probability of making is 0.9, and I'm making how many? I'm wanting to make at least one. So it's going to be from 1, 2, or 3. And then I'm going to be missing none of them. If I make one, I'm going to be missing 2. All the way up to making all of them and missing none of them. So that would be what the formula would look written out in FRQ. If you're doing it in MC, you could just put it directly into your binomial formula. And you would actually get 0.999, which, by the way, you can see at least one of the three shots is 1 minus, so you could have done it a little simpler as well, of saying 1 minus the probability of missing all of them, of missing all, which is this here, and that's where I get the same one here. But you could definitely put into your binomial calculator, and that's going to be a binomial CDF. And the binomial CDF is going to be x equals 3. Of course, the lower bound is going to be 1, and the upper bound is going to be 3, because that's going to be, I want to make between 1 and 3. And, of course, the probability of making would be 0.9, because your probability, this is asking what's the probability of making, sorry. So I'm making sure that I put 0.9. The 0.1 was missing. C says, what's the probability that Michael makes the first shot, but not the second or the third? So that's making the first, missing. So that's just simple, straightforward probability, which is 0.9, and then 0.1, which is just going to be 0.009. Okay, so for this one, let's go ahead and I want you to draw a chart. If you haven't drawn a chart already, go ahead and do so. So you're going to go ahead and I'm going to put English, not English, history, not history, and then my total. It says of the 10,000 freshmen, so I've got 10,000 here. 7,000 must take English, so I'm going to put 7,000 here, which means that's 3,000 here. 6,000 must take history, so 6,000 history, and 4,000 here. And 5,000 must take both. So I'm going to put 5,000 here. And then obviously 6,000 minus 5,000 is 1,000. And this is 2,000. And this is going to be 2,000 just by adding and subtracting. Now that it's set up, it should be a lot easier for me. What's the probability that the selected student must take English? So selected student is going to be 10,000 on the denominator. So I'm going to probability of English is just going to be 7,000 out of 10,000. And then, of course, I'll put 0.7. What's the probability the selected student must take both English and history? So that's just going to be English and history. And it's, again, selected student. So that's out of 10,000. So this is going to be English and history. And if you're not sure of how to write it, you can just write the English part out. You can write probability English and history. And you won't get anything wrong. And then you're going to have 5,000 out of 10,000, which is 0.5. Suppose you learned that a selected student must take English. What is the probability that the student must take both English and history? So this means of the English, so the English denominator is 7,000, because what I'm looking for is these guys here, and that's it. So of those 7,000, what's the percentage that is going to have to take a history and English? So those are going to be 5,000, and that's going to be 0.714. Are the outcomes must take English? And so this is going to be probability of English and history given English. Or you say history. Obviously, it's got to have English, but really it's history given English, because obviously if I've given English, then I'm going to have to take English too. So it's history given English was 0.714, and English was 0.7. And then, of course, if I say, are the outcomes of English and history independent? So what's the probability of history? The probability of history is, of course, 0.6, because it's 6,000 out of 10,000. Probability of history given English is 0.714. And so I would say if probability of history given English equals the probability of history, then they are independent. But you can see the probability of history given English is not equal to the probability of history, because I have, of my work that I have here, I can say those are not the same. So therefore, we would call them dependent. Or not independent would be another way you could put it. Answer the question posed in Part D if only 4,200 students had to take English. So now they're saying if I have 4,200 out of the 7,000 students instead of 5,000, that's going to be 0.6. And then yes, the probability of history given English would be 0.6, and the probability of history would also be 0.6. And because they're the same, then I would say yes, independent. Okay, for example 6, let's look here and see. This is the tardy one. This one sets up nicely as a tree diagram, but I find that if you can set it up as a, if you can set it up, as a table, it just helps you a little bit better. So I'm just gonna do this. I'm gonna set it up as a table. I mean, you can set it up here, and we can say Rudy. Fawn, late, on time. And let's fill in the information we have. So it says we have Rudy works the list 30% of the day, so I'm just going to put it out of 100 total. Fawn does it 70% of the days. Rudy fails to get the list in 10% of the time that she works, and so that would be she's 10% times 30, and so 10% times 30 is going to be 3, and then that means 27 out of 30 is on time. And then it says Fawn is, just make sure I got that, 30% of the days, 10% of the time, yes. And then it says Fawn much better manages to get it 92% of the time, so 8% of the time she's late, so 0.08 times 70, which is going to be 5.6, and then that's going to be 64.4. And then you just add everything up from here, and you have your probabilities ready to go. So this is going to be obviously 8.6, and this is going to be 91.4, if I did everything correctly. Now, you're welcome to do a tree diagram. If you did a tree diagram, let me just quickly put it for you. Rudy, Fawn would be 0.3, 0.7, and then on time, late, and on time would be 0.1, 0.9, late, and on time would be 0.08 and 0.92. So you can see it's the same thing, except I went ahead and did the math to be able to make up my chart. So it says, though, the problem, what I'm looking for, let's say your principal SAC and the tardy list is late. So we know it's late, so it's right here. It's this column I'm looking for because we know it's late. So my denominator is 8.6. And it says, what's the probability of Rudy? So Rudy is going to be 3 over 8.6, and 3 over 8.6 is 0.3488. So if you were doing it on the tree diagram, you would do late, and late would be here. And what you would do is this. You do Rudy, so it'd be the probability of Rudy and late, or excuse me, Rudy given late, which is the probability of Rudy and late, over the probability of late. And then you would do the probability of Rudy and late, which is 0.3 times 0.1, over the probability of both of them being late. So Rudy being late and Fawn being late would be both of them together, which is going to get you exactly what you got here. But you can see, I think it's just quicker and easier to do the table. So that's why I did it there. Example 7,